to have with us Dr. Mike Rosenberg. Dr. Rosenberg graduated from Swarthmore College in 2008 with a bachelor's in physics and a minor in history. His thesis was on modeling X-ray absorption spectra in photoionization experiments on Z. He then earned a PhD at MIT in 2014, working in Rich Petrosso's group with a thesis on ion kinetic effects in shock-driven implosions and magnetic reconnection in laser-produced plasmas. After that, he joined the University of Rochester's Laboratory for Laser Energetics, primarily to run direct drive ICF experiments on the NIF, including laser plasma interactions, hot electron preheat, and polar direct drive implosions. Talk. He also won a thesis award, the Rosenbooth Outstanding Doctoral Thesis Award from APS DPP in 2016. And also a couple quick notes. So on the HED Center's website, we've now posted all the talks from 2020. Not the videos yet, but there are many slides that are available. And we hope to have the videos soon. And also this talk is being, if you're uncomfortable with that, please log off. And if you have any questions, please enter them in the chat field and I will read them at the end of the talk. And also, please be aware that it's an unclassified meeting with lots of external people logged in. Otherwise, I'm very much looking forward to the talk, and please take it away, Mike.
All right, thanks a lot, Paul, for that introduction and for inviting me to speak today. So I'm presenting on the MegaJoule direct drive campaign NIF experiments on the pathway to megajoule yield. This is a campaign of focused experiments that allows us to understand the physics of direct drive inertial confinement fusion at scales that are relevant to ignition and will ultimately lead to high performance direct drive implosions on NIF. So most of the talk will be spent going over experimental results from the three main physics issues that we need to study at NIF scale. Those are related to laser energy coupling and symmetry, hot electron preheat, and laser imprint. So in summary, current megajoule scale experiments lay the groundwork for high yield direct drive implosions on the NIF in the 2020s. Extrapolation of direct drive implosion performance from omega to ignition scale depends on dedicated physics experiments on the NIF. The MegaJoule direct drive campaign on NIF includes three primary physics areas: hot electron preheat, which has been measured at close to levels thought to be tolerable for direct drive implosions. It's shown to be partially mitigated using mid-Z layers and also shown to originate from stimulated Raman scattering. Implosion symmetry and energy coupling, including crossbeam energy transfer, has been shown to be controlled using wavelength detuning, contoured shells, and beam pointing. Laser imprint experiments have produced X-ray radiography data to benchmark models of imprint-related instabilities and partially mitigated using multi-FM smoothing by spectral dispersion or high-Z layers. And current NIF capabilities limit high-performance polar direct drive implosions to low convergence exploding pusher-like implosions, though a stage set of proposed facility improvements will ideally allow for increased convergence and yield. So this work is a large collaboration of people at several institutions, including a number of folks at LLE as well as at Livermore, and a number of other institutions both here in the US and internationally. So the rest of the talk will go as follows. First, I'll introduce laser direct drive inertial confinement fusion, talk about scaling and how that motivates our experiments on the NIF. Then I'll get into the details of the MegaJoule direct drive campaign in these three main physics areas: laser plasma interactions and hot electron preheat, laser energy coupling, crossbeam energy transfer, and polar drive symmetry, and laser imprint. And then finally, I'll talk briefly about current high-yield polar direct drive implosions and what we see as a potential pathway to reaching megajoule yield. So as many of you know, there are three main approaches to achieving inertial confinement fusion and high yield in the laboratory. Laser indirect drive uses lasers to illuminate the inside of a high-Z hohlraum, which creates X-rays that drive a capsule implosion. Pulse power magnetized fusion, otherwise termed magnetic direct drive. You may have also heard of it as MagLif. Uses very powerful currents to drive strong magnetic fields that implode a cylindrical target. And then here in the center is laser direct drive, where lasers directly illuminate a spherical capsule, which drives ablation and implosion of that capsule containing fusion fuel. So most direct drive experiments that go after high performance, albeit at reduced scale relative to what we think is required for ignition, is done at the Omega laser, which is designed for laser direct drive experiments. So Omega experiments are done at around 25 or 30 kilojoules with capsules that are typically around 900 microns. This is about 70 times less laser energy than is available on NIF, with capsules that are about a quarter of the size that we would expect to use in ignition scale experiments. But Omega has several advantages for direct drive experiments. Firstly, we have 60 beams arranged symmetrically around the chamber to uniformly drive the capsule, with circular beam spots that are roughly matched to our target dimensions. Beam smoothing is near state-of-the-art, including 2D smoothing by spectral dispersion and polarization smoothing. And we have a cryogenic target capability for direct drive. In contrast, NIF has a laser energy approaching 2 megajoules that's a lot closer to ignition scale, but is not yet optimized for high-performance direct drive implosions. So one thing is that NIF, being designed for indirect drive, has beam ports that are concentrated near the poles in order to illuminate the inside of a hole round, but which makes it a little more challenging to directly drive our capsules. The beams have to be defocused quite a bit to match direct drive target dimensions, and beam smoothing is fairly limited, both of which degrade beam quality. And there isn't currently a cryogenic direct drive target handling capability. Despite these limitations, NIF can be used to great advantage to learn about direct drive physics at ignition relevant scales now, and with some improvements to the facility, we'll be able to work our way towards high performance implosions. Current direct drive cryogenic implosions on Omega extrapolate to yields at around 570 kilojoules at 2 megajoule laser energy, assuming that hydrodynamic scaling is valid. So as I mentioned, Omega experiments are done in the energy range of about 20 to 30 kilojoules and produce yields in the few hundred joules. So hydrodynamic scaling holds that yields increase roughly like laser energy to the 4/3. So as you go up by about a factor of 70 in energy, you would end up with yields in the several hundred kilojoule range. But there are several physics mechanisms that can cause a deviation from that, those that don't necessarily obey hydrodynamic scaling, and these are things that we need to get a handle on at the appropriate scale. So in this context, there are two major thrusts of the direct drive ICF research effort, which encompasses experiments on both Omega and NIF. The first of which, of course, is just to improve implosion performance on Omega. We've made tremendous progress in the last several years with yields increasing by about a factor of 3 in that time scale. So the idea here, of course, is that if you have better performance on Omega and you do the same extrapolation, you'll end up with a higher projected yield on NIF. And in addition to that, we conduct focused physics experiments on both Omega and NIF in order to assess or validate this extrapolation. So this is where the MegaJoule direct drive campaign fits in, which consists of experiments in areas of physics that are primarily related to laser plasma interaction that don't necessarily obey hydrodynamic scaling and really have to be studied at the relevant scale. So these include issues related to laser energy coupling, crossbeam energy transfer, and hot electron preheat. We also do experiments to study and mitigate laser imprint. We do some direct hydroscaling experiments to validate that. And we also test our codes in an integrated way and try to achieve relatively high yields in low convergence implosions. And in fact, we can quantify the plasma conditions in the corona of our direct drive experiments and show that the experiments we're doing now on NIF approach or achieve scale lengths that are relevant to ignition and are inaccessible on Omega. So this table summarizes simulated plasma conditions at the quarter critical density region out in the corona. I use the quarter critical region as a representative location in the corona where a lot of laser plasma interactions occur. These include stimulated Raman scattering, which can both scatter light as well as produce high energy electrons as that light is coupled to light waves and plasma waves. Crossbeam energy transfer and energy loss mechanism happens in this range. So this is just a representative region of the corona. For ignition scale designs, we expect scale lengths of around 600 microns and temperatures of 3 to 5 keV. As I'll describe in a couple of slides, we developed a planar platform that achieves the relevant scale lengths and temperatures. And we do implosion experiments on NIF, but at slightly reduced scale, which come close to the necessary scale length and temperature. On Omega, however, of course, we're about a factor of 4 lower in capsule dimensions and consequently about a factor of 4 lower in the relevant scale length. So this is why it's important to be doing experiments on NIF that are trying to replicate ignition relevant conditions. All right, so now I'll get into the details of the MegaJoule direct drive campaign and these 3 areas of focused physics experiments. So the first one I'll talk about are laser plasma instabilities and hot electron preheat, which has been studied in both planar and spherical geometry to determine preheat levels and to assess preheat mitigation at ignition relevant scale lengths. So what we're concerned about with preheat is illustrated in this cartoon on the left. You know, as I just mentioned, there are laser plasma instabilities that can occur at densities around and below quarter critical density, which can generate hot electrons. Those electrons can stream into the implosion, deposit energy in the DT fuel, and make it more difficult to compress, which is problematic for reaching ignition. So we've developed 2 experimental platforms to study this. We have a planar platform, which helps us understand LPI mechanisms and to study hot electron production. And we have a spherical platform to study how hot electron energy is actually coupled to implosions. So as I showed, these experiments essentially replicate or nearly replicate the scale length and temperature that we expect to reach in ignition implosions. The planar experiments are closer to that, but are at a slightly different laser geometry than we would have in an implosion. The spherical experiments have an appropriate laser geometry, but are a little bit short in scale length. So there's still a little bit of extrapolation that we have to do to go from this to projecting preheat in an ignition relevant case, and I'll talk about that towards the end of this section. So the planar LPI experiments firstly established the predominance of stimulated Raman scattering as a hot electron source. We can see that in looking at the scattered light spectra, an example of which I'm showing here on the left. So this is a time-resolved optical spectrum from one of our planar experiments, and we observed 2 notable features in the spectrum, one of which is a sharp, slightly red-shifted half harmonic feature. This is at a little bit more than twice the incident laser wavelength. This feature is indicative of an absolute SRS instability, very close to quarter critical density. And then we also see a lower wavelength feature which corresponds to SRS at densities below quarter critical. Notably, this spectrum is quite a bit different than what we typically see on Omega, where we have a doublet half harmonic feature and no SRS whatsoever. And in fact, on Omega, this is indicative of the 2 plasmon decay instability. So this experiment illustrates right off the bat the importance of doing experiments at the appropriate scale, since as we found in going from Omega to NIF, we go from a regime that's dominated by TPD to one where instead SRS is the dominant hot electron producing mechanism. So these experiments were also valuable to study the intensity scaling of preheat as well as its mitigation using silicon ablators. So this plot shows the conversion efficiency of laser energy to hot electrons as a function of the simulated laser intensity at quarter critical density. So we observe an onset of hot electrons around intensities of 510 to the 14, which increases more or less linearly from there. We did experiments with a plastic ablator with beams at different angles of incidence, which showed a modest difference. And then we see a much more significant difference when we go from plastic to silicon ablators. So silicon has the effect of reducing the amount of hot electrons by or more than a factor of 2. And you can also think of it as pushing out the intensity threshold at which we start to be affected by hot electron production. So it's important to point out that when we're talking about preheat and implosions, that depends not only on how the hot electrons are produced, which is what's shown here, but it depends on how the hot electrons diverge and couple their energy to the inner portion of the shell. So we implemented a PDD implosion platform using germanium-doped layers. This was adapted from a concept that was developed on Omega to diagnose preheat deposited in the inner portion of the shell. So the principle of this experiment is illustrated here on the left. Essentially, we have a set of identical implosions with the same capsule dimensions, the same laser drive, and so on. But some of the capsules contain a germanium dopant over the inner layer. And the idea is that the coronal plasma conditions will be identical, the LPI will be the same, and therefore that the source of hot electrons in the corona will be the same. But based on the presence of this higher Z material, the experiments containing the germanium dopant will produce more hard X-rays as shown in these calculations. So we can therefore use the difference in hard X-rays between these different experiments to tell us directly how much hot electron energy was deposited in the germanium doped layer. So the NIF experiments show the expected variation of hard X-ray signal with germanium dopant and that the LPI is identical. So here on the left is the time-resolved SRS scattered light signal from 3 different experiments with different amounts of germanium dopant. This is more or less identical as we expected, which indicates that we have the same LPI and that we can conclude that the source of hot electrons that are produced in the corona is in fact the same. And therefore, when we examine the time-integrated hard X-ray spectra, we can infer that these differences are only due to the presence of the germanium dopant. And in fact, we see that as we go from a pure plastic ablator to one that has a thinner germanium doped layer and then a thicker germanium doped layer, we in fact see more hard X-rays. So this is a nice sanity check that the platform is performing as we expect. And we can use this data quantitatively to map out profiles of the deposition of hot electron preheat in the shell. So hot electron preheat in these NIF implosions is inferred to be about 0.2% of laser energy over the inner 80% of unablated shell. And it's about a factor of 2 lower when we make use of a silicon layer in the ablator. So this plot here shows the cumulative hot electron fraction as a function of a radial position within the shell. The data points are extracted from the difference in hard X-ray signal between doped and undoped experiments. And this curve represents a Monte Carlo fit of hot electron energy deposition based on that data. And so we see that as there's a significant amount of hot electron energy absorbed in the ablated plasma, which actually isn't a problem for our implosions. And then as we get into the unablated shell, which is the part that we care about, we're seeing about 0.1 to 0.2% of laser energy deposited as preheat, most of which is in the outer portion of that unablated shell. And notably, as I mentioned, if we don't use a silicon layer, it's about a factor of 2 higher. So this again illustrates the efficacy of silicon that we first demonstrated in the planar platform. Notably, the absolute amount of preheat that we're getting is close to the limit that we think we can tolerate for direct drive ignition designs, which is around 0.15%. It depends somewhat on the adiabat of the implosion and other parameters, but it shows that we're roughly in the ballpark of how much preheat we think can be tolerated. So we also did a hydrodynamically scaled version of this experiment on Omega, which actually shows a similar fraction of laser energy coupled to the inner shell as preheat. So these Omega experiments were a factor of about 3.5 smaller than what we used on NIF. The laser energy was reduced by a factor of 40, but was scaled appropriately. And we note that over the inner portion of the shell, like we saw on NIF, On Omega, we also have about 0.2% laser energy deposited as preheat. So this is an important result that supports the validity of hydrodynamic scaling for warm implosions, which is to say that preheat wouldn't cause any deviation from hydrodynamic scaling. One important difference that we see across the two scales is that the attenuation of hot electrons in the outer ablator is quite a bit different, and this seems to be an important effect. So you'll notice on NIF that a much larger fraction of the total amount of hot electron energy is dumped into the ablated plasma, whereas on Omega that's less of an effect. So this is likely due to the fact that on NIF there's just a lot more plasma for those hot electrons to deposit their energy in on the way from the quarter critical or slightly below quarter critical density region to the unablated shell. And this effect is something that we're going to have to account for when we try to estimate preheat in a cryogenic implosion where a lot of this CH is replaced by DT, and the DT is somewhat less effective at attenuating hot electron energy. So overall, the goal of these NIF experiments is to determine the parameter regime, really the intensity that produces acceptably low levels of preheat. So the experiments I've talked about so far were the ones done at an on-target intensity of 10 to the 15, either without silicon or with silicon. We've done some experiments at lower intensity, which shows about a factor of 2 reduction with a 25% reduction of intensity. Over the rest of this year, we intend to fill out these curves, both with and without silicon at higher and lower intensity, which will provide us a pretty complete data set and allow us to infer the intensities that we think we'll be able to work at for our implosions. So we can also use this data to estimate what sort of preheat levels we would expect in an ignition scale cryogenic implosion at these intensities. So there are some subtle differences between the warm and slightly subscale implosions that we've done so far and an ignition scale cryo implosion. And so we can start at these results and work our way through these various differences to try to infer how much preheat we would expect. So we can start at the 0.2% of laser energy into preheat in these implosions. As we go higher in scale, the planar experiments help us know that we would expect maybe a factor of 1.5 to 2 more preheat as a result of that. However, the ignition implosions actually converge more, which helps with preheat because there's less solid angle for the hot electrons to interact with, so we'll get a reduction from that. The presence of DT in the ablator will be less effective at screening hot electrons, so probably see more preheat because of that. But silicon has been found to be very effective, so we'll get a benefit from using that. One other thing that I haven't yet touched on in this section, but is very important, is that given the relatively poor beam quality on NIF, the results that we've gotten so far represent a near worst case scenario for preheat. And as beam smoothing is ultimately improved, as we'd like to do, we should derive a benefit from that. But overall, we think that based on the data so far at intensities of 10 to the 15, the amount of preheat that we're getting looks to be roughly okay. But we have further experiments planned to help us pin down these various multipliers here. We'll do larger scale experiments to determine this. We have experiments planned to test the effect of convergence. And we also plan to test silicon dopants in contrast to silicon layers and see how much of a benefit that has on preheat mitigation. All right, so now switching gears to laser energy coupling and symmetry. So these experiments have been conducted in spherical geometry platforms at a variety of convergence ratios. We started with a kind of standard polar drive, ablatively driven implosion platform using fairly thick shells. These experiments were conducted primarily to study crossbeam energy transfer and its mitigation using wavelength detuning. These were at a convergence ratio of around 12. We have a thinner shell, lower convergence experiments. Sometimes these are called exploding pushers, although that's not quite technically correct, but we use the shorthand sometimes. These are at a convergence of around 7. And then we also have a solid sphere radiography platform which of course doesn't converge at all, being a solid sphere. And we use this by, we measure the trajectory of the converging shock to tell us about energy coupling and CBET. And so there are trade-offs between these different platforms. Essentially, as we go to higher convergence, we're getting a more integrated implosion experiment, a more strenuous test of our models, bringing in a number of different physics effects. On the other hand, as we go to low or no convergence, we're sort of stripping away some physics related to hydro instabilities, for example, but enables us to do a better focused energy coupling experiment. So in polar direct drive implosions, crossbeam energy transfer is a primary energy loss mechanism, and it occurs predominantly near the equator. So CBET is something that I'll be talking about throughout this section. Just as a little bit of background, what happens in CBET is we have multiple beams that interact in the corona of a directly driven target, and rays from one beam that have kind of skirted the target and are on their way out interact resonantly with rays that are on their way into the target. And the way this happens is there's a resonant interaction through ion waves that effectively transfers energy from the incoming to the outgoing ray. So this costs us energy when driving the implosion. And additionally, in polar direct drive, it causes symmetry problems as well. So in polar drive, we have to repoint some of the beams to illuminate the equator. And so in that equatorial region, we have a number of overlapping beams at fairly oblique incidence. And this configuration gives rise to crossbeam energy transfer more so than what we see on the pole. So we've done calculations that show this. It kind of confirms our intuition. And so CBET it's not only an overall energy coupling problem, but it's a symmetry problem as well. And one way that we've explored to try to mitigate CBET is by introducing different wavelengths between the interacting beams, which makes that resonant process less efficient and allows us to recover some of that lost energy. So we've done this in PDD implosions using cone swapping to produce hemispheric wavelength detuning across the equator. So NIF has a terrific capability of allowing different cones of beams to be driven at different wavelengths. But a drawback to that currently is that this is hardwired to be symmetric about the equator, which isn't optimally effective for direct drive. So we designed experiments where in one hemisphere, we repointed polar beams towards the equator and vice versa, so that by introducing a wavelength shift between cones, we were able to affect a wavelength detuning over the equator where CBET is most problematic. So these implosions were done with a wavelength shift of plus or minus 2.3 angstroms and demonstrated partial mitigation of CBET in good agreement with our 2D calculations. So the simulations told us that we should have expected the introduction of wavelength detuning to make our implosions more prolate, and also to cause a buildup of mass along the equator based on where the energy was now being deposited. And our experimental X-ray radiographs bear that out. So we see both the implosion go from fairly oblate to less oblate, maybe even a little prolate, and we see this equatorial band of mass around the equator. So this was a very successful demonstration, a proof of principle experiment that shows that we can use wavelength detuning to control and affect symmetry. But this is really just the first step. And going forward, we've found a couple of different things. One is that while plus or minus 2.3 angstroms is the current limit, we find that we need more than that, at least based on our calculations, in order to greatly enhance energy coupling. So something above plus or minus 3 angstroms is when we start seeing a much larger effect. And a plus or minus 6 angstroms would do us tremendous amounts of benefit. Additionally, we want to be able to flexibly map different colors onto different ports, which is a capability that's coming online in the next year. So this will allow us to avoid having to do this cone swapping and producing a fairly distorted shape. One challenge that we encountered in our implosion experiments is that we've been unable to simultaneously model the ablation front and the inner shell trajectories, which may suggest a problem from laser imprint. So in these experiments, we obtained X-ray images either from self-emission, which corresponds to the position of the ablation front, or alternatively from a radiography, which tells us about the position of the inner surface of the shell. And so as we measure those trajectories and compare to simulation, we find that while the backlit trajectories are fairly well matched with an implosion velocity, according to that measurement, correct to within about 1%, the self-emission images show a slower velocity by about 9%. And in fact, by the end of the laser pulse, we can infer that the apparent thickness of the shell is quite a bit larger than what our simulations suggest. So this is thought to be related to laser imprint and the subsequent Rayleigh-Taylor growth. This is a 2D calculation with laser imprint. And you can see that in flight towards this time of interest around the end of the pulse, while the inner surface of the shell is fairly intact, the region corresponding to the ablation front is seriously perturbed. So imprint could be affecting our interpretation of this experimental data, which was ideally intended to tell us about energy coupling. So really, this concern about imprint has led our energy coupling campaign to lower convergence implosions to try to eliminate that contribution. So lower convergence implosions, which are almost by definition less sensitive to imprint, are now being used to assess and improve energy coupling and symmetry. So in comparison to our standard implosions, we have these low convergence exploding pusher-like experiments, which are at larger shell diameters, but with much thinner shells. And as a result, rather than being primarily driven by compression, the initial shock is a much larger player in the hotspot formation and the resulting yield. The convergence is about a factor of 2 lower. And while both of these platforms are sensitive to energy coupling, unlike the implosions, which are more sensitive to instabilities, the thinner shell, lower convergence implosions are thought to be less susceptible. So we first used this platform to study shell contouring as a means to control symmetry and improve energy coupling along the equator. So as a reminder, near the equator in polar drive, we have very oblique incidence. We have a lot of seabed. It's just inherently challenging to couple laser energy to the equatorial region. So one way that we can compensate for that and ideally produce a symmetric implosion and recover an implosion velocity that doesn't vary with polar angle, we can design a shell that's thinner at the equator than at the pole. So that's what we did. This was based on simulations of a previous experiment that showed significant pole-equator asymmetries in flight. And so we designed a shell that was about 4 microns thicker at the pole than at the equator. General Atomics did a terrific job matching fairly closely what we requested here. And the result of the contoured shell was that we were able to eliminate 5% in-flight P2 asymmetry, which is in agreement with our post-shot calculations. So these are X-ray self-emission images looking along the equator, advancing through different times during the laser pulse. And we note that by the end of the pulse, the experiment without the contour was starting to become a bit oblate, whereas with the contour, the shell was quite a bit closer to round. And so when we quantify the different mode amplitudes, we find that the P2, which is essentially the equatorial radius versus the average radius, we find that that's about 5% without the contour, and it's effectively eliminated with the contour. And both of these were reasonably well matched by our post-shot simulations. So the next question that you'll have is, well, what effect did that have on performance? We think that the effect was positive, although unfortunately this was complicated by a difference in gas pressure unexpectedly between the two experiments. So the second experiment that had the shell contour actually produced the same yield as the experiment without the contour, but the gas pressure on this one was reduced by about 18%. And our simulations tell us that that should have cost us about 30 or 40% in yield, which we can take to mean that the contour was effectively boosting yield by 30 or 40% in order to recover this. So that was an encouraging result. We did additional experiments using this platform that demonstrated control of symmetry and energy coupling, not through changes to the target, but by changes to the laser, including laser pointing and pulse shaping. So these two experiments use both a different pointing scheme in terms of remapping how the different cones are positioned onto the capsule, as well as using different pulse shapes, either a linear ramp to a flat top or an exponential ramp to a flat top. And the experiment below also allowed for different peak power in the different cones. So this was expected based on our pre-shot simulations to produce a significant difference in the implosion shape. So the first experiment was expected to be quite a bit more oblate, almost like a tuna can kind of shape, sort of flat near the pole. Whereas the second experiment was predicted to be a lot closer to round. And the experimental images bear this out as well. So in the first experiment, we do see this flattening near the pole. It is starting to become oblate towards the end of the pulse. Whereas in the second experiment, it is quite a bit closer to round. So that was a good result. However, the yields in these experiments came in pretty much exactly the same, whereas our calculations predicted that they would be different by about a factor of 2. So it seems like the improvement in shape didn't translate to an expected improvement in yield. So we began to look into this in post-shot simulations. There's some indication that laser imprint may still be playing a role, especially with this exponential to ramp pulse. So that's something that we're continuing to work on understanding. Looking ahead, we have experiments planned for next year to test the new flexible color port mapping capability to more effectively mitigate seabed in polar drive using wavelength detuning. So as I mentioned before, the wavelengths on NIF are currently hardwired to be symmetric about the equator. But in the next year, we'll newly have a capability to map different wavelengths onto different cones so that we can implement different 2-color or 3-color techniques, which are predicted to increase absorption and yield. So you can see in this table a couple of different 2-color and 3-color mapping schemes and the expected impact on the implosion. So we estimate that the absorption will improve without wavelength detuning. It would be somewhere in the high 70s% of laser absorption. Whereas with these 2-color and 3-color schemes, we think we can get up into the low 80s and consequently improve the yield as well. So the third energy coupling platform are the solid sphere experiments, which are completely impervious to imprint and instabilities and provide an isolated test of energy coupling and seabed modeling. So the way this platform works is we have a solid sphere at target chamber center driven by most of the NIF beams, and we have some of the beams directed to a copper backlighter, and we have an X-ray imager off behind the capsule, behind the sphere, which allows us to image the difference in absorption due to the density jump across the converging shock. So we used laser pulses shown here. The main sphere drive is an exponential ramp to a flat top, and the backlighter pulse was varied in time to allow us a long record over which to observe the shock convergence. So the shock trajectories that we infer from the radiographs and as well as the X-ray flash time are in good agreement with 2D Draco simulations. So an example of the radiographs is shown here on the left. The bright spot represents the backlighter, and then the dark ring is the shock front. And so you can see as we advance in time going from right to left, this feature is of course getting smaller. And so we've extracted the angle average position of the shock front, which correspond to the data points in this plot over here. And in comparing that to our Draco simulations, we find very good agreement with both the trajectory and the time of shock collapse. So this is a nice demonstration that we seem to roughly have a handle on energy coupling in this platform, at least at this one intensity. So we have further experiments this year to scan different laser intensities and also to test modeling of pulses that have multiple shocks, with the idea that the subsequent shocks after the first one being launched during the main drive are more representative, more susceptible to crossbeam energy transfer and give us more information on our modeling of that. And on top of that, we also have direct hydroscaled versions of these experiments planned for Omega for a test of hydrodynamic scaling of energy coupling. All right, so now I'll switch gears again and talk a little bit about laser imprint. So these experiments have been conducted on NIF to benchmark imprint models and to develop mitigation techniques. We have two different platforms that we use for that, one of which is a planar imprint platform that we use to diagnose imprint in single beam or single quad configurations. And then we also have a spherical cone and shell radiography platform that we use to study imprint in a situation that's more representative of an implosion with many overlapping beams. So the ultimate goal of these experiments is to determine requirements for laser and target solutions for imprint mitigation, essentially how much beam smoothing is necessary, what kind of target mitigation techniques are needed, and even to test some of those out directly. So our planar single beam imprint experiments have produced excellent data to benchmark imprint calculations, although we do observe a discrepancy relative to our simulations. So here at the top are our face-on X-ray radiographs corresponding to imprint from a single beam on a foil without any beam smoothing. And we see as we advance in time the growth and merger of Rayleigh-Taylor features seeded by laser imprint. And we can quantify the ρr modulation corresponding to those. And we observe that relative to our simulations, the calculations actually predict a faster rate of Rayleigh-Taylor growth and an earlier saturation than what we see experimentally. So there's some disagreement in different analyses of this data, depending on background subtraction or exactly how you infer the backlighter spectrum. But overall, there are some discrepancies here that we need to understand. We recently developed X-ray sidelining to measure the trajectory of the foil as it moves. Since if we're not getting the acceleration right, then that would of course affect our growth of these instabilities, and so that's something that we're working through analysis as well. We've also used the planar platform to test imprint mitigation using a multi-FM smoothing by spectral dispersion on one quad. So the radiographs here show the difference between the standard 45 gigahertz SSD on NIF and the multi-FM SSD. So in these radiographs, the vertical stripes correspond to a pre and post modulation, which is essentially a reference for the growth of ρr modulation as the foil accelerates. And the horizontal stripes represent instability growth seeded by imprint. So by eye, you can tell that the multi-FM is producing a more uniform optical density map, a more uniform map of ρr modulation. And it's qualitatively in agreement with what we see in simulated radiographs. As we quantify the ρr modulation, we can infer a difference, an improvement, as we go from the standard 45 gigahertz SSD, which are the red points, to the multi-FM SSD, which are the blue points. And these are roughly in agreement with the expected quantitative difference that was predicted by our simulations. We are running into a bit of a noise limit, perhaps a resolution limit as well. And so a next step for the planar imprint campaign may be the use of Fresnel zone plates in order to achieve resolution that's about a factor of 3 better than what we're getting now. Our cone and shell imprint experiments have been used to assess imprint from multiple overlapping beams and also to test HEDS overcoats to mitigate imprint. So these experiments used a thin plastic shell with an embedded gold cone, some of which had a thin, very thin gold coating applied to the outside. And in these experiments, we used a single beam incident on the backlighter as a soft X-ray pre-pulse to expand the coating, which has been shown in experiments at other facilities to be important for most effectively using the coating to mitigate imprint. And then the main drive came in like 10 nanoseconds later. And so we see in our radiographs the difference between experiments with and without the gold coating. So particularly as you see as we advance from early to later time up to down, without the coating, we can very clearly see the growth of Rayleigh-Taylor features seeded by imprint. And without the coating, those are much less pronounced. With the coating, those are much less pronounced. And we can quantify the power spectrum from each of these experiments, and we observe that for frequencies corresponding to wavelengths between about 20 and 50 microns, we can see a reduction in the spectrum there. So it's indicative that the overcoat is having an effect. We're still analyzing these results, but it is a promising first result for imprint mitigation using overcoats on NIF. All right, so before I move on to the last section, I just want to quickly go over what we've learned so far in the campaign. In the area of energy coupling, symmetry, and CBET, we've shown that these can be controlled using wavelength detuning, shell contouring, and beam pointing. Going forward, we intend to test flexible color port mapping to more effectively use wavelength detuning. We have further solid sphere experiments to benchmark energy coupling models at different intensities with different numbers of shocks. The LPI and preheat experiments have shown that SRS is the predominant hot electron source. We've shown that this is close to tolerable levels for intensities around 10 to the 15, and we've shown that silicon is very effective at mitigating preheat. Going forward, we have further experiments planned to aid our extrapolation of preheat levels to what we would expect in an ignition scale cryo-implosion. And for imprint, we've developed two effective platforms for studying imprint and imprint mitigation. We've shown a benefit using multi-FM SSD and high-Z coatings. Going forward, we need to work on benchmarking our 3D calculations of imprint. We want to apply higher imaging resolution, and also as target solutions are developed to apply those to the platforms that we've already been using. All right, so finally, I'll talk a little bit about our current high-yield PDD implosions and what we're looking at as a potential pathway to reaching megajoule yields. So we are currently doing high-yield polar drive implosions. These are conducted in the exploding pusher-like platform. This has been a very fruitful collaboration between LLE and Livermore to develop high-yield neutron sources, and we've routinely produced yields in excess of 10 to the 16. So these experiments, like the exploding pusher-like experiments I was describing earlier, are using pretty large capsules. The most productive ones have been between 4 and 5 microns, with shell thicknesses of about 22 to 28 microns. You can see the table of different laser energies, powers. We've tried different pulse lengths and so on. So we've been able to get yields in excess of 10 to the 16. We continue to work on different designs with different pointings, different pulse shapes. We're still working on optimizing shell diameter and so on. In the near term, we expect to be able to optimize these experiments to reach yields of about 2 times 10 to the 16 or about 50 kilojoules of yield. In the near term, we expect that improvements in wavelength detuning, including in flexible color port mapping, which again will become available very soon, will facilitate better energy coupling and performance in polar drive implosions. So I already talked a bit about how this capability will let us put different wavelengths on different cones. We can test out different configurations to more optimally mitigate CBET and improve energy coupling in PDD. But we expect that we need not only this flexible capability, but also an enhancement in the absolute magnitude of wavelength detuning. So currently for our best performing implosion, we calculate that we have absorption in the sort of 81 to 82% range. And then as we introduce the flexible color port mapping, and then as we crank up the wavelength detuning, our calculations tell us that we'll be able to produce a significant enhancement of absorption into the mid 80s and even upwards of 90% if we're able to push this to plus or minus 6 angstroms. And the yield would go up correspondingly along with that. So this is just one example of proposed NIF facility improvements that would go hand in hand with steps up in convergence and in implosion performance. So currently we're working with low convergence implosions. We're trying to optimize symmetry and energy coupling as best we can. We're working on validating our codes. We think that we can reach yields around 50 kilojoules. With flexible color port mapping and ideally an enhancement to wavelength detuning, as well as dedicated polar drive phase plates, which can also help better control symmetry. We think that with these low convergence implosions, we'll be able to enhance energy coupling, push absorption over 85%, and produce yields in the 100 kilojoule range. And then looking quite a bit farther out, we hope to implement a cryogenic target system for PDD to add enhanced beam smoothing or target solutions to mitigate laser imprint. And this is what will allow us to really push convergence ratios into a range that's similar to what we're doing now in omega cryogenic implosions. We'll be able to significantly, of course, increase compression and hopefully reach alpha heating and burning plasma conditions with yields in the several hundred kilojoule to megajoule range. I'll just briefly touch on diagnostics, which are important to improve understanding and demonstrate that we have a handle on these implosions and guide us towards improvements. So one example of this is a scattered light time history diagnostic, which we're implementing at a variety of angles around the NIF target chamber. The idea is this will help us understand the angular distribution of scattered light, which is predicted to be fairly complicated in polar drive, both as a function of polar and azimuthal angle. So this diagnostic measures time resolved scattered light in different wavelength bands corresponding to various instabilities, including measurements near 351 nanometers, which is mostly affected by seabed. We measure SRS as well. So there are currently 11 units operational. There will be 15 within the next year or so. And so again, these will help us greatly constrain our modeling and tell us if we're in fact improving energy coupling in the way that we expect to do. All right, so in conclusion, current megajoule scale experiments lay the groundwork for high yield direct drive implosions on the NIF. Extrapolation of direct drive implosion performance from omega to ignition depends on dedicated physics experiments at the NIF scale. I talked about hot electron preheat, how that's been measured at levels close to what we think are tolerable. We've shown that it's partially mitigated with mid-Z layers and shown to originate from stimulated Raman scattering. We showed partial control of symmetry and energy coupling, including crossbeam energy transfer using wavelength detuning, contoured shells, and beam pointing. And we've done imprint experiments to benchmark modeling and to assess mitigation using both laser and target techniques. And while current NIF capabilities limit high performance PDD implosions to low convergence experiments, we expect that a staged set of facility improvements that we've proposed will allow for increased convergence and yield. Thank you for your attention.
Thank you, Mike. Thanks for the great talk. So please enter your questions in the chat field if you have any, or if you're having trouble typing, you can just maybe just enter a Q and I'll call on you. And otherwise, please unmute yourselves and we can give our speaker a nice round of applause.
Thank you. Any questions?
Hello, this Mike.
Yeah.
Might there be some crosstalk between seabed and SRS since they're occurring at similar densities?
That's a good question. I don't know if we've considered an LPI process that, you know, interacts through both of those. The most obvious way that we think about seabed affecting SRS or hot electrons is simply through the fact that it's reducing intensity. You know, and as we mitigate seabed, that's actually something we're going to have to keep an eye on. Is as we mitigate seabed, intensities will go up, and we would expect to get more hot electrons than what we're getting now. I'm not sure if we would expect any, you know, interaction between electron waves and ion waves or something like that.
Thank you.
Any other questions?
Hi, it's Damien Swift here. Can you hear me?
Yes.
Okay, so I actually had several questions. I've got to sign off in a minute. Can I just ask one of them quickly, though? So looking at the pulse shape where you found advantages going from a trapezoid to something that's a flat top with a ramp starting it, could you say a little bit more about the merits of that pulse? And the reason I'm asking is that that looks to me like, at least to the outer part of the ablator, it's not generating a shock. That looks like, sorry, but does it really still count as an exploding pusher?
Yeah, so the exploding pusher terminology isn't completely applicable to these experiments. It's really, I mean, there is ablation and some compression. It's predominantly shock driven, which is maybe a better way to describe it. But there is still a strong shock driven in that exponential ramp pulse. It is definitely fast enough to do that. The exponential pulse was thought to produce a slightly faster implosion. We do see some evidence of that. That's one of the reasons we expected to see an improvement in yield, as well as the improved shape that was generated in part using that pulse. So those are some of the reasons why we expected to see improvement, but that sort of pulse also is likely more susceptible to imprint to the degree that that's still a factor at even those low convergences and high adiabats.
So Heather commented that we're starting to call them ablatively driven thin capsules.
Yeah, thank you, Heather. That is a better description.
I do wonder if the reason behind that is that you're producing a ramp rather than a single shock early on, and so the material you're ablating at later times is higher densities, and maybe that's why it produces a higher pressure that translates to a higher implosion velocity.
Yeah, I'll have to look into the simulations and see exactly what difference in shock behavior was predicted.
It's very interesting. I had other questions. I'll email you about later.
Yes, please. Anyone feel free to email me or type questions or whatever, and I'll be happy to answer.
Any other questions? Well, if not, let's thank our speaker again.
All right. Thank you very much, Paul. Thanks everyone for listening.